Hi there, welcome back to this channel. In this video, we're going to be starting our first calculus series, um, and I'm going to be introducing you to calculus. All right, we're going to begin from the scratch, the fundamental idea. You see, this idea of calculus is a very, very ingenious idea that I would not advise you to just master rules or reduce it to mastering principles or rules or methods, and then you think that is all about the topic. Now, it is more than just mastering of rules and methods of both differentiation and integration, right? So, although we're going to be doing a lot of principles, yes, there are rules, but it should not. This idea is bigger than reducing it to just rules. So it is very important that you understand the the basis of this of the idea behind calculus. Now you see the word calculus actually means to calculate. Is that okay? From the word from which calculation is gotten. All right. So and it actually refers to small pebbles, which was used in the calculation that was used in the creation of abacus. You know, the abacus machine that is used for counting and doing sums. And all right, so that's the word from which calculus is originated. And then it is in full called infinitesimal calculus. So infinitesimal standing for very small. So it means that we are calculating with very, very tiny, um, you know, differences. So in fact, it is the mathematics of change. That is one way to define it. It's the mathematics of everything that change. So we talk about rate of change and all of that. So, and in this case, we are going to be discussing changes. We're going to be dealing with changes that are very, very small, that are infinitesimally small. Is that okay? As small as 0.000001. So if you have seen that video, I'm going to link it in the description on limits. So you are going to see what we have discussed about very tiny changes. All right, and we are going to be employing the idea of limits here. All right. So now, what do we deal with in calculus? Now, we're going to be dealing with both differentiation, and integration. Now, in differentiation, what we want to do is that we're going to be taking the rate of change of something with respect to, we're going to be taking the rate of change of a function with respect to a particular variable. And while in integration, we're going to be talking about the area under a particular shape. Is that okay? All right. Now, we are going to first be starting with the differential calculus, which is differential calculus or differentiation. Now, how did this idea originate? You see, the idea of differential calculus actually came about, was, first discovered by two scientists who discovered it independently. Those are Gottfried Leibniz and our Sir Isaac Newton. All right. So the convention that we use today, the YDX convention, which is what I'll be teaching you with, is according to Gottfried Leibniz. All right, because that of Isaac Newton's was quite. I mean, it was not as easy to understand as Gottfried Leibniz, but the ideas were almost the same. And by the way, Isaac Newton discovered it first, and so there was just this banter about who discovered it first, whose work it actually was, and whose work it wasn't. All right, so we are going to be talking about the idea of differentiation and how it actually originated. Now, you see, it came about that, the idea of slope that we talked about. We've talked about it in our pre-calculus video. So if you want to take the slope of this line, for example, this line is a linear, this is a line, right, which is a product of a linear equation. A linear function gave rise to this, isn't it? Now, if I want to take the slope of this graph, of this line, what I need to do is take a particular y value and take a particular x value, and then take a particular the x value that corresponds here, x1, and the particular value that corresponds here. This will be y1, and here y2, here x2. So with this, you know that this is going to have a negative slope, and in fact, you see that it's sloping downward, so it's going to show you that it's a negative relationship between the y and x variable. So, but what I'm talking about is the fact that to take the slope of this thing, I just say m is equal to what? Y2 minus y1 over x2 minus x1. So that is what? Changing y over changing x. And that was what we talked about in the precalculus series. So basically, it's rise over rho. And it is easy to compute here. So, and the reason why it's easy is because the slope of this graph is constant throughout. It's not changing throughout the line, the entire line. Is that okay? And that's the one thing with linear functions. Their slopes are constant. And I'm going to prove that to you in just a minute. You are going to see why we say their slopes are constant. Now, the problem now arose when scientists tried to, compute the. So if I had a curve, for example, if I had a locus, for example, and I want to compute the rate of change, you can use any locus, you can use these, any part of the circle, any curve, any sector of the circle, any of the arc, any part of the arcs of the circle. So I just want to use this to show a positive, I wanted to show a positive relationship, right? So now if I want to calculate the slope of this curve, we're going to see that, scientists noticed that, both of them, they noticed that it actually changed at every point. So the slope of this thing was different from the slope at this point, it was different from the slope at every of the regions. Why? Because it's a curve. And this is the reason why it's different from a line. Is that okay? A line, every point is beside each other. Is that okay? Every point, a line is the distance between two or more points, right? So every point, every point is beside each. Every point is, is arranged. It's just beside each other. Do you understand? So, and that's what we call a straight line. But this is a curve. It is different. So every point is at an angle different from another point. So that is why the slope will change at each point. All right. So they came up with the problem of trying to there arose a problem of trying to find the slope of this thing at a particular point. So let's say we want to take the slope of this thing at this point. So we notice that the slope of this thing cannot be taken because we are going to have only one point here. And for a slope, we need at least 2 points. Is that okay? So we said that to take the slope here, if you take the slope here, you are going to get the same slope as when you take it here, as when you take it here, or as when you take it in this tiny place. Do you understand? So we said the slope will be constant. But here, to take the slope, we need 2 points. But they notice that we can only get a point here. So it means that we can only have a tangent to this curve. So if we have a tangent to this curve, how do we take the slope of a tangent? The slope of a tangent is impossible. So how do they now resolve to finding the slope of the tangent to this curve? All right. So the idea they came about was a very brilliant one, which was to do this. Now they erected another line which is parallel to this, so which is going to be a secant. We call it a secant, a line that cuts touches the two ends of that cuts through the two ends of a circle of a curve. It's called a secant. So they took drew a secant that would be parallel to this tangent. So when you draw a line, a secant that is parallel to this tangent, they would obviously have the same slope. All right, but we are not taking the slope of this line. We are taking the slope of this curve at this point. That's very important for you to know. We are taking the slope of this curve at a particular point because it was noticed that the slope, and in fact you can see it, that the slope changes per time. At each point. No 2 points have the same slope. Is that okay? I want you to listen to my words very carefully. No 2 points on this curve have the same slope. Since no 2 points have the same slope, it means that you can only take the slope at each point. All right. So now what they came up with was to erect draw a secant that will be parallel to that, parallel to this tangent. So since this secant is parallel to the tangent, it means that the slope of the secant will be equal to the slope of the line of tangent. Is that okay? Now, but you know that to take for a slope, we need 2 points, which are y2 minus y1 and x2 minus x1. All right, so now what they came up with is this. It is not possible to take the slope of the tangent because we can only have a point here, and 1 point here. So what did they do? Now, this was what they did. They came about. Now, if you notice, for this our secant, for example, for this our secant, now let me make it better. Let me put it together in a better way. If I have something like this, and I want to take the slope here, the slope of this tangent, right, at this point. So what they did was to draw a secant line. I hope it's parallel. So to draw a secant, let's just assume it's parallel to this line. All right. So they wanted to so they drew a secant that is parallel to this. Now, if you want to take the slope of this secant, that is quite easy. What you do is take a point x here, which is a point on the curve. You can take it on the curve. You take a point on the curve. This is going to be x2 now, and this will be x1. Now, if you take on this point, you take the slope here. To take the slope, the y value will be y1 here, and here is going to be x1. Okay, let me clean that. This is going to be, this point here is going to be y2. All right. Now, this point here, we can call it, this here is our x1, and the difference between here and here, we can call it change in x or h. You will see this in some of the textbooks. Is that change in x is used or h is used. Now, I'm going to be using either one. Maybe I prefer to use h. Now, it means that y1 here is going to be a function of x1 here, isn't it? So since it's a function of x1 here, it's going to be f of x. Is that okay? So if the difference between here and here is h, it means that x2 is therefore x1 plus h, which is x plus h. Right now, we're not using x2, we can just use x in each case, isn't it? All right, so this place is x plus h, that is the difference between x and this point. These 2 points is h, so this point will be x plus h if the difference between them is h. You understand that? All right, then y2 here is going to be a function of x2, and since x2 is now h plus x, then this place becomes what? Function of x plus h. All right, so this is what we have in this case here. All right, so now it means that our slope here, now remember that it is slope of secant, not yet the slope of this tangent. Now the idea they came about was to do this, was to reduce the slope of this tangent to bring it closer and closer to this tangent. Now listen, first we said that the slope of this secant is going to be what? y2 minus y1. Now y2 is f of x plus h minus y1, which is what? F of x, and over x2 minus x1. x2 minus x1 is going to be h, isn't it? That is change in x or h. Is that okay? Either way you put it. So now this is the formula for the slope of secant. Now, the idea they came about, both of them, was to do this independently though, was to do this, to bring the slope of this secant closer and closer to this point of the tangency. They brought the slope closer and closer to this point. So you notice that since all of these lines are parallel to the secant, it means that they are going to have the same slope. Remember that for parallel lines, m1 is equal to m2, isn't it? All right. So they brought it closer and closer to this point here. So even at this point here, in as much as we can have more than 1 point to take our slope, this line is still going to have the slope of the secant. All right. Now, therefore, they came about the idea of what is called a limit. Now, what is that limit? You know that When does this secant become the tangent? The secant become the tangent when the line is only touching the curve at one point. The secant, I repeat, this secant becomes this tangent when it touches it at only one point. When as much as touching at least 2 points, it is going to still be a secant. But when does it become a tangent? When the change in x, has become 0. That is, we have zeroed it into this point, that there is no longer any difference. We have only 1 point in each case. Do you understand? So since we now have only 1 point in each case, at that point will be m tangent. So and what was the idea they came about? The idea they came up with was to say that the end point of this m secant. Now, m secant is going to be the slope of this secant line, which will be parallel to the slope of the tangent. But at the end of the day, this m secant, we cannot take the slope of tangent, but the slope of secant is going to get closer and closer to the slope of the tangent. Let me repeat that. I said that we cannot take the slope of tangent, as I said earlier, but we can take the slope of the tangent. So the slope of the secant. So the slope of the secant is going to approach, as we bring it closer and closer to the tangent, is going to approach the slope of the tangent as much as possible, so that the slope of tangent is going to be its limit. The slope of tangent, that is m tangent, is going to be the limit of the slope of secant as h approaches 0. So when does h approach 0? How does h approach 0? That is, the change in x becomes 0. So there is no change in x. We have only 1 point for x. We have only 1 point for x and only 1 point for y. So that is going to be the slope of the tangent. The slope of tangent is going to be the limit of this slope of secant. It's not going to get to that point. You know, in this limit video, I talked about the fact that limit is the point beyond which your function cannot get or cannot go, but at which your function, the limit is the point, the function, or the value which your function cannot get to, but is approaching or getting closer and closer as possible with 2. All right. So the m secant, the m tangent, is going to be the limit of the slope of secant as h becomes 0. Because when h becomes 0, what we have is what? Is a tangent. Do you now understand? So the slope of this tangent at this point is going to be the slope of secant of, so m tangent, let me just put m tan, is going to be, what is m secant? M secant is this. So it's going to be the limit as h approaches 0 of what? F into bracket x plus h minus f of x over h. And this becomes what we known as the first principle of differentiation. The first principle of differentiation. All right. So we're going to be utilizing this first principle. But there are 2 ideas around this first principle. So I'm going to be using those 2 methods. There are 2 methods of resolving the first principle. And I'm going to be using those 2 methods to quickly solve some questions. But I hope you understand the idea of how the first principle came about. All right. And I want you to comment down in the comment section below if you did understand it. And if you don't understand it, you can always text me on WhatsApp. This is my WhatsApp number. I'm going to be solving, or some of my students are going to be solving invariably all JAM questions so far on differentiation. So I will enjoin you to subscribe to the channel if you have not already, in order not to miss out of any of those contents. All right. So I said that let's use, if I said f of x, let's use the first principle to resolve a particular function. For example, x. So if I want to differentiate this, so we call it to differentiate this function. How do I differentiate this function? What I'll do is, I'm going to say my slope is going to be, if this is f of x, then f of x plus h here being an infinitesimally small change in x. Is that okay? All right, so you can also see dx. You could see x plus dx. Is that okay? All right. So it means that our f of x plus h will become x plus h, isn't it? All right. That is, there's a small change in x. All right. So recall that our m seconds is equal to what? F of x plus h minus f of x all over h. And what is our f of x plus h? F of x plus h is what? Is x plus h. So that becomes x plus h minus, what is f of x? Minus x over h. So f prime of x. Okay, I didn't talk about that. F prime of x is what we use to denote differentiation. So is either use dy dx, or you say f prime of x, or you say dy dx. This is the this is another notation. Capital D, capital Y, then small letter x, or sub x, d sub x, y, capital Y. That is also dy dx. Or you see y prime if you are using the y function. All right. So f prime of x now becomes this, so that f prime of x is now equal to this minus this is 0. This minus this is 0, yes. So that h, we now have h over h, and this becomes what? 1. And that is our answer. Now the second method to this is this. If I told you that y, which is f of x, is equal to x, now what you do is this. Add that infinitesimal small change in x. As in, for example, if x was 2, and I added 0.0000000000002, 2.0000000, limitless number of 02 and 2 are the same, are pretty much the same. All right, so if I add that little change in x, it's going to result in what? A little change in y. I call that dy or delta y. Is that okay? So you see some textbook use this notation or delta x. Is that okay? But I prefer to use this. Now it's equal to x plus dx. So a little change in x brought about a little change in y. All right, remember that what we are looking for is f prime of x or dy dx. So in this case, I'll make dy subject. So dy becomes x plus dx. Now follow me, it's very, very simple. Then I bring this guy to this side. Notice I put it in brackets because if I have a longer function, there is a different way by which I will solve it. So I have dy will be equal to x. What I mean by that is that this minus is going to impact my function inside there. So plus dx. What is my y? Initially, we said that y was x, right? So minus x is what we have. So this takes care of this, and then we have dy equal to what? Dx. So what do we do from here? We divide through by what? Dx. Then we have dx. Okay, nothing cancels here. This one takes care of this, so that dy dx is equal to what? 1. Okay, one thing I forgot was this. Here, before we get, what we actually have here is actually f of x. Is that okay? So, the f prime of x, the slope. But what we now need to do is to take the limit, the slope of this tangent, to this line. Remember that this is linear, so you do not have a tangent. Is that okay? So the slope of the tangent will now be what? The limit as h tends to what? To 0 of this f prime of x. I hope that is clear. So the limit here is still 1. Why? Because h is not here, so h cannot tend to 0. So the same way here, the next thing we do is what? We'll take the limit of dy dx as dx tends to what? To 0. So if we take that limit, we still arrive at 1. I want you to flow with me. Let me solve other functions that we have that this value we actually have impact upon. So for example, if I say find if y was x cubed plus minus 2x squared minus 1. And I said solve this using the first principle, right? So what do you easily do? You say that we are going to add a small change in x and add a small change in x here. And then if we add small changes in x here, it's definitely going to impact the y, right? So it means that a small change in x will lead to a small change in y also, which is the y is equal to x plus dx all cubed minus 2 into bracket x plus dx squared minus 1. All right, notice that there's no x here, so there's no little change that will affect that. So from here, we can say that y plus dy is going to be equal to, now we are going to expand this. This becomes x plus dx into bracket x plus dx squared. We're going to expand this separately. That's why I separated it here. So minus 2 into bracket. If you square this, excuse me, you know, this is x plus dx. We add the dx to x, then square it all together. Do you understand? Here, if this was like 3, for example, if x was 3, this would be x, this would be 3 squared, that is 9. Do you understand? So here, when we add the little change, it should be added directly to x, not just this guy squared. I hope you understand that. So x plus dx, if we add the little change, it will not still change it from being 9. Is that okay? All right. So if we square this, x squared plus 2x dx plus dx all squared, dx squared minus 1. So from here, we can have that y plus dy will be equal to, when we open this bracket, okay, we can't open yet. Let's put this here, so that this squared is going to be equal to this, right? So we have x squared plus 2x dx plus dx squared minus 2. No, now we can use 2 to open this bracket, minus 2 to open this bracket. This becomes minus 2x squared minus 4x dx minus 2 dx squared all minus 1, right? So from here we can now open the brackets with this guy, so that we have y plus dy to become x times this to give us x cubed plus 2x squared dx. This times this, that is, this times this, we got this, then this times this to get this, then this times this will give us what? X dx squared. I hope you're following me. Then plus this times this to give us x squared dx plus this times this to give us 2x dx squared. Now this is dx that is carrying squared now, right? Then plus this times this to give us what? Dx cubed. Dx squared times dx, that's dx cubed. Then minus 2x squared minus 4x dx minus 2 dx squared minus 1. Is that okay? So from here, we can, okay, let's still continue. Let's simplify this one so that we have y plus dy will be equal to, from here, we have that x cubed is staying alone, plus, now we have 2x squared dx. Let's see if we can find another x squared dx. So this and this, right? No. This guy and this guy will give us 3x squared dx. 3x squared dx, because this is 2x squared dx plus 1x squared dx. Is that okay? Then plus x dx squared plus 2x dx, so that's also what? 3x dx squared, all right? So this and this are gone. Then we are left with plus dx cubed minus 2x squared minus 4x dx, then 2 dx squared, okay, minus 2 dx squared minus 1. There are no common, no like terms here. So what do? We take that y to the other side because we are looking for dy dx. So dy becomes x cubed plus, these are the steps. Is that okay? When you have simplified for that to the list, then you take that y to the other part of the equation. So when you take it to the other part of the equation, what do you have? This 3x squared dx plus 3x dx squared. Make sure that you are careful when you're writing this, because the expressions are so much, so it's possible, mistakes are likely, so be very careful. Minus 2x squared minus 4x dx minus 2 dx squared minus 1, then minus y. So notice I put my y in the bracket again, so that we have dy will be equal to x cubed plus 3x squared dx plus 3x dx squared plus dx cubed minus 2x squared minus 4x dx minus 2 dx squared minus 1 minus, now remember that our y was this, right? So put that in brackets. That was x cubed minus 2, okay, x cubed, let's put that here, minus x cubed minus 2x squared minus 1. All right, that's our y, right? So what do? The minus is going to open this bracket, or minus 1 will open the bracket. So let's extend here. So we have dy will be equal to x cubed plus 3x squared dx plus 3x dx squared plus dx cubed plus, minus 2x squared plus 4x dx minus 2 dx squared minus 1, then minus all of this. You know, this is x cubed minus 2x squared minus 1. All right, minus all of this will give us minus x cubed. Minus times minus plus 2x squared plus 1. Is that okay? So from here, you notice that plus x cubed will take care of minus x cubed. And with first principle is always like that. Is that okay? You always see that the first term is going out. Then let's see other like terms. Looking at this, we have x squared. Is there any other guy with x squared? Yes. We have minus x squared and plus x squared. Plus 1 and minus 1 has also gone. So what do we have left here? We now have dy to be equal to 3x squared dx plus 3x dx squared plus dx cubed plus 4x dx minus 2 dx squared. All right, what do we have now? What do we do from here? Since there are no like terms any longer, what do? We divide both sides by what? Dx, because that is what we're looking for. This is the gradient, isn't it? Changing y over changing x. So this becomes, now this is not yet the gradient of the tangent, because this is going to obviously be a curve, you know, a parabolic curve, x cube function, all right? So dy dx will become what? If we divide through by dx, okay, let's just put dy through by dx, dx over dx over dx over dx over dx. Dx will take care of 1 here, dx goes here, will remain 2 here. Is that okay? Then here, it should remain 1. Then here, it takes care. So we have dy dx will become 3x squared plus 3x dx. There's one more remaining here because one left. Plus dx has become squared now, no longer cubed. Plus 4x, 1 has gone. 1 has gone. All right. I mean, the entire thing has gone. The entire thing has gone. So minus 2 is, then here is remaining 1 dx. All right, from here, the next thing we do, just remember from here, after dividing through by dx, what did we do? We took the limit of this function. So we'll take the limit as our dx approaches 0, because it is at the point where it is approaching 0 that it becomes slope of tangent. You understand? Slope. So we'll now take the limit. I hope you understand what I'm saying. I said we'll take the limit of this function now, because that is now the slope of the tangent to the curve at the point where we are taking it. All right. So that slope becomes the limit as dx tends to 0 of dy dx. So it means that dx becomes 0. So at dx approaches 0, what do we have? 3x squared plus, this one becomes 0. So we have 3x into bracket 0 plus 0 plus 4x minus 2 into bracket 0. All right, so what do we have therefore? Dy dx therefore becomes 3x squared. This one becomes 0, this one becomes 0, plus 4x, and that is the answer. All right. So our answer is going to be 3x squared plus 4x. And you can always verify that using what is called the general principle. The general principle uses the chain rule. And the general principle is this. Let's quickly just talk about the general principle, and that will be the end of this video. So the general principle says that if I have x raised to power to a particular exponent, dy dx, therefore, if y is equal to this, then dy dx is going to be, n will come down, nx, n raised to power minus 1, n raised to power n minus 1. So what this says is that we'll bring this n down times x raised to power n minus 1. Is that okay? And that is the case. So in another case where we have a coefficient for this x, so that we have ax, for example, is this raised to power n is the same. If y is equal to this, then dy dx as x tends to 0 will become an x raised to power n minus 1. So nothing has changed, only that we are multiplying this coefficients by that power that was brought down. Is that okay? All right, so this will be the end of this video. In the next video, we are going to be talking about other methods of differentiating. See you in that next video. And do well to subscribe to the channel if you have not already. And God bless you.